On May 4, 2023, a Ukrainian Patriot battery fired a single interceptor into the night sky over Kyiv and destroyed a Russian Kh-47M2 Kinzhal. This chart visualizes a stark collapse in defensive performance. In May 2023, the intercept rate against the Kinzhal was 37%. By March 2026, when Russia launched 40 missiles at Lviv, not a single one was stopped, an overall success rate of just 6%. The physical weapon dropping out of the sky did not change between these two dates. The airframe, the rocket motor, and the payload remained identical. Russian leadership spent years marketing this system as an unstoppable triumph of modern engineering. The anxiety surrounding these weapons often centers on the word hypersonic, which simply means traveling faster than Mach 5. Speed alone is not the threat. Intercontinental ballistic missiles have been re-entering the Earth's atmosphere at speeds exceeding Mach 20 since the late 1950s. Hitting an object moving that fast is difficult, but it is a solvable geometry problem provided the target follows a predictable ballistic arc through space. The strategic value of modern hypersonic weapons comes from maneuverability within the atmosphere. They force air defense networks to calculate an intercept geometry that constantly changes. When an object pushes through the atmosphere at Mach 7, the air ahead of it cannot get out of the way fast enough. It compresses violently, converting kinetic energy into intense thermal energy. This compression creates a plasma sheath around the vehicle, where temperatures reach 3,000 degrees Celsius. That is hot enough to liquefy standard aerospace materials like titanium and aluminum almost instantly. Older re-entry vehicles solved this by using a blunt, rounded nose. This geometry forces the shockwave outward, keeping the most intense heat off the surface, while thick ablative coatings burn away. A blunt body falls predictably. It generates almost no aerodynamic lift, meaning it cannot alter its course to evade an interceptor. This diagram illustrates the structural solution required for atmospheric maneuverability. To steer, a vehicle needs sharp leading edges to generate lift. Those sharp edges focus all the extreme friction onto a razor-thin area. The outer layer utilizes ultra-high temperature ceramics. These rapidly conduct the heat away from the stagnation point, so the edge does not melt. Meanwhile, embedded fibers allow the material to flex, absorbing the mechanical shock of pulling intense G-forces without shattering. Prolonged, maneuverable flight at Mach 10 relies entirely on these specific advances in materials science. Engineers apply this structural science using two distinct design philosophies. Russia's Kinzhal is an aeroballistic missile. It is a modified short-range ballistic missile carried to high altitude and released at supersonic speeds by an aircraft. This visualization compares the two approaches. On the left, the Kinzhal relies on the brute force of a rocket motor. Its cylindrical shape is not optimized for lift. When it executes an evasive dive in its terminal phase, it generates immense drag, bleeding off the speed that makes it dangerous. On the right is China's DF-17, a hypersonic glide vehicle. A rocket booster carries it to the upper atmosphere, where the glider separates and begins an unpowered, flatter trajectory. This glider is a wave rider. Its geometry traps high-pressure gas directly beneath the hull, allowing the vehicle to literally surf on the shockwave it creates. This lift allows it to perform skip-glide maneuvers, pulling up into thinner air to reduce friction, then diving back down, maintaining its velocity without relying on an engine. The DF-17 is an operational weapon, currently deployed with the People's Liberation Army Rocket Force. The aeroballistic Kinzhal sacrifices kinetic energy every time it turns. The waver rider design of the DF-17 allows it to maneuver while gliding across the atmosphere. Defensive architectures were built around specific geometric assumptions, dividing the airspace into two distinct layers. This cross-section shows point defense systems like Patriot covering the lower atmosphere against aircraft and cruise missiles, while systems like THAAD operate in the exo-atmospheric zone to intercept traditional ballistic arcs. A hypersonic glide vehicle cruises perfectly between 40 and 60 kilometers in altitude. It sits above the effective ceiling of Patriot and below the floor where THAAD is optimized to operate. A depressed trajectory creates a secondary advantage against ground-based early warning radars. Terrestrial arrays operate strictly on a line of sight. The physical mass of the Earth curves, blocking the beam from detecting a low-flying glider over long distances. A weapon traveling at Mach 10 covers 100 kilometers in about 30 seconds. By the time the vehicle crests the radar horizon and becomes visible to terrestrial sensors, the defender's warning time drops from minutes to a matter of seconds. These weapons do not rely on jamming or radar-absorbing materials. They exploit pure planetary geometry to strip away decision time. Interceptors like the PAC-3 MSE employ a hit-to-kill methodology. They do not use explosive proximity warheads. They must physically collide with the incoming threat. This radar tracking interface demonstrates how a clean interception works. The system monitors a target on a smooth ballistic arc and calculates a highly stable prediction cone to place the interceptor exactly where the target will be. When an aeroballistic missile executes a sudden non-ballistic dive during its final approach, that prediction cone shatters. The fire control software is forced to drop the invalid track, reacquire the target, compute a completely new vector, and redirect the interceptor in flight. Executing this recalculation loop against an object covering 2 to 3 kilometers every second pushes the computational limits of the system. This explains the severe drop in Ukrainian intercept rates. By late 2025, Russian engineers uploaded a new terminal flight algorithm to induce more erratic maneuvers, without upgrading the physical missile. Physical hardware sets the boundaries of flight, but software dictates unpredictability. The intercept window becomes an algorithmic conflict fought in milliseconds. Even with precise radar placement and optimal software, defense batteries face a rigid economic constraint. The March 2026 attack on Lviv illustrates this perfectly. Here is the cost ledger. An advanced PAC-3 MSE interceptor costs roughly $4 million per shot. An incoming decoy drone costs about $20,000. Adversaries launch waves of hundreds of cheap drones specifically to saturate the airspace, forcing the battery to exhaust its finite magazine of multi-million-dollar interceptors. The actual hypersonic strike is timed to arrive exactly when the defense battery is empty and locked in a vulnerable reload cycle. The most advanced physics and tracking software in the world are irrelevant if a defensive system is systematically bankrupted before the real threat arrives. Closing this geometric gap requires abandoning terrestrial radar limits and moving the detection architecture into low Earth orbit. The ionized plasma sheath that complicates a hypersonic weapon's internal sensors also creates a massive, blazing infrared signature. This visualizes the hypersonic and ballistic tracking space sensor constellation. Orbiting satellites bypass Earth's curvature, maintaining unbroken line of sight on the glider's thermal bloom. This tracking data feeds naval vessels, allowing glide phase interceptors to engage the weapon mid-course, before terminal evasion. Russia introduced the Kinzhal to bypass existing American defenses. Instead, it accelerated the development of a far more complex orbital tracking network. Warning times have collapsed. The 30-minute window political leaders historically relied upon to verify threats and authorize responses is gone. Mastering extreme speed is no longer the primary objective. The advantage goes to the military that successfully integrates advanced materials, orbital geometry, and autonomous software into an unbroken, instantaneous defensive network.